Very good morning to everyone. This is Karthikeyan from MAMSE School of Engineering. In this lecture, EC8652 Wireless Communication, Department of ECE, third year students. Today, we are going to discuss about the topic two-ray model. In previous classes, we have discussed the large scale losses and free space path loss models. Now, today, the two-ray model or ground reflection path losses. In mobile communication, the two-way ground reflection model is more accurate than free space propagation model. The two-ray propagation model considered the direct path, reflected path, and geometric path. These models hold good for large scale strength predictions in wireless systems. For example, we can see the block diagram. Let HT and HR, that is a transmitted height of that antenna and received antenna. A transmitted antenna height and receiver antenna height, the T and R are transmitted receiving antennas. The received total electric field is at which would be sum of direct and reflected electric field components. Therefore, the electric field is a total electric field is equal to losses, electric field loss plus ground reflected path of electric field. In this case, the E naught is the free space field at a distance of D naught from the transmitting antenna. Then E field would be given as E of D comma T is equal to ED divided by D into the cos of omega C into T minus D divided by C. Now let us move to the ground reflection, that is a two-ray model. For two-ray model, the received power at a distance D from the transmitter can be expressed as a received power into the distance is equal to transmitted power into the gain into the transmitted height of the antenna and the receiver height of the antenna divided by the distance D power 4. The path loss from two-ray model can be expressed in dB as path loss dB is equal to 40 log D minus 10 log GT, that is a transmitted gain, plus 10 log received antenna gain, plus 20 log transmitted antenna height, plus 20 log receiver antenna height. Now we can see the reflected two-ray model. Here, in the reflection of the wave, the incident angle pi I is equal to the reflected angle pi r. The reflection coefficient, that is a gamma, is represented the ratio of reflected voltage incident to the incident voltage intensity. In this perfect conductor, reflection coefficient is unity. So the reflection coefficient now we can be calculated. So the reflection coefficient, which is a unit less, it is nothing but ER, that is a reflected voltage intensity into e power j pi r divided by incident voltage intensity. So the total electric field is expressed in this two-ray model. The total electric field is equal to mod of losses of electric field plus ground reflected path electric field. In this method of the transmitter and the receiver separation, the antenna height, the electric field components of both direct waves and the ground reflected wave, the path difference. Now the transmitter to receiver separation larger than the HT plus HR in the mobile environmental. Then according to that Taylor series approximation, this path loss difference del is expressed as a del equal to d double dash minus d dash. So we can find out the path loss del in between the electric field. So del equal to 2 pi del divided by pi. Now the calculation of the tau d and pi del depends upon the path difference, that is a del in the value in the practical cases of where the transmitter to receiver separation is larger than the transmitted height and receiver height of the antenna. In this model we can find out the reflected path and geometric optics models. In the two-ray ground reflected model, in the difference between the distance and the height of the antenna and the height of the receiver antenna, into the find out the electric field losses. So it reflected models is more accurate than the series propagation model. It prediction in the wireless system. Now the next video lecture we have to discuss the link budget design, that is a link budget design in the path loss models. Thank you for watching this video.